The current project is a time series analysis of weekly mail earning in Australia from 1956 to 1991. The current data set is available in Time Series Data Library dataset and contains 142 observations from 1956 to 1991. It is a quarterly observation of weekly mail earnings in all industries. There are two variables in the dataset: real average mail weekly earning and average mail weekly earning. The average mail weekly earning was measured by Australia Bureau of Statistics Average Weekly Earning Survey, which is designed to measure the level of average earning in Australia at a point in time. For the purpose of the current report, only real average mail weekly earning variable was used for analysis. This dataset was used to observe the changes in the average mail weekly earning. A possible set of ARIMA models were identified, and the best model was chosen to make forecasts of the weekly mail earnings for the next 5 years. The time series plot of the dataset showed a considerable variation in weekly mail earnings. There is a definite upward trend in the series from 1950 to 1970s. After that, there is a steady increasing and decreasing around 1975 to 1991. In addition, the plot suggests that the neighboring values are closely correlated. A scatter plot of the series also suggests that there is an upward trend in the data. The correlation between the earning is 0.981, which denotes a highly positive. The ACF plot for the series displays a geometric pattern that is slowly decreasing. This is a pattern that can be seen in the ACF of non-stationary series. In stationary series, the autocorrelations tend to decay to zero at higher lags. The ACF of the current dataset therefore indicates that the data is not stationary. The PACF plot for the series shows 5 significant lags and dies out in the subsequent lags. A significant regression equation was found in the linear trend model with an R-square of 0.915, indicating that 91.5% of the variance in the data is explained by the model. Furthermore, it estimated that the slope is 4.735. This suggests that the weekly earnings increased by 4.735 every quarter. The p-value for the model was low, suggesting a significant relation between the variables. Normality test for the residuals of the linear model was conducted. The QQ plot shows that the majority of the data is fitted into the straight line pattern. However, some outliers can be observed in the plot. The tails of the regression line shows that the data is not a snug fit in the straight line pattern. This can indicate non-normality. This was tested using the Shapiro-Wilk normality test. The high p-value indicates the stochastic component of the linear trend model to be normally distributed. So we conclude that the residuals are normally distributed. The ACF of residuals for the linear model shows several spikes that decreases in a slight wave-like pattern. These spikes are not within confidence boundaries at several lags, implying that there were autocorrelations left in the residuals of the linear model. The PACF of the linear trend model also shows that there are four. A significant regression equation was found in the quadratic trend model with an R-square of 0.949, indicating that 94.9% of the variance in the data is explained by the quadratic model. The p-value for this The normality test for the residuals of the quadratic model shows it to be normally distributed. The plot shows that the majority of the data fits into a straight line pattern. However, some outliers can be observed in the plot. The tails of the regression line shows that the data is not a snug fit in the straight line pattern. This can indicate non-normality in the residuals of the quadratic model. Shapiro-Wilk test, however, yielded a p of 0.053, which indicates that the stochastic component of the quadratic trend model is normally distributed. ACF and PACF plots of the residuals of the quadratic models were generated. The ACF shows several spikes that decreases in a slight wave-like pattern. These were not contained in the confidence bounds. This implies that there is positive correlation at these specific lags. The PACF of the quadratic trend model also had 4 significant lags. The residual analysis of the linear and quadratic trend models suggests that these two models are not the best fit for the current data and that we should further explore ARMA or ARIMA models. The ACF plot of the weekly earnings series had indicated that the data is not stationary. The Dickey-Fuller test for stationarity was conducted to test this. The test yielded a high p-value, which implies that the data is non-stationary. The Box-Cox transformation was applied on the data. After the transformation, the Dickey-Fuller test was performed on the transformed data again. The p-value was still high, suggesting that the transformed data is still not stationary. The data was differenced twice. After first differencing, the Dickey-Fuller test was conducted again. The output of the test indicated that the data is non-stationary as p is greater than 0.05. After the second differencing of the data, the Dickey-Fuller test was performed on the second difference data. This time, the output of the test showed a significant p-value, thus making us conclude that the data is The ACF and PACF of the differenced series was plotted. The PACF shows 3 significant spikes. This suggests that we should include ARIMA 320 model as one of our candidate models. The EACF and BIC table suggests that we should choose ARIMA 324, ARIMA 325 and ARIMA 425 as the candidate models. All 3 of these models are supported by the BIC table. To choose a model that is most suitable for the data, we will need to perform some more. A model diagnostic test using maximum likelihood was performed on the ARIMA 324. All the coefficients for the model A model diagnostic test using maximum likelihood was performed on the ARIMA 325. All the coefficients for the model except MA5 were found to be significant. A parameter estimation test using maximum likelihood and residual analysis was performed for ARIMA 325. The residual analysis shows that there is an outlier in the data as presented in the histogram and QQ plot. The ACF and PACF shows that there is no significant autocorrelation in the residual in this model. The Leung box test gave a p-value of greater than 0.05, which suggested that the null hypothesis of uncorrelated error term cannot be rejected. A model diagnostic test using maximum likelihood on the ARIMA 425 showed only MA3 coefficient to be significant. The AIC and BIC tables for the candidate models suggest that ARIMA 324 is the best fitting model for the current dataset as its AIC and BIC values is lowest compared to the other models. So based on the analysis that was conducted in these slides, we can conclude that ARIMA 324 is a very good fit for our weekly wages time series data. Using this model, we forecast the wages for years 1986 through 1990. The information in this plot and table suggests that the ARIMA 324 model for the series predict an increasing and decreasing pattern in the weekly male wages for the next 5 years. The plot also shows that the model can be used for accurate prediction.